what did we start doing yesterday? Yesterday we started finding evidence between dualities, between gauge theories and string theories. Okay? So our goal is to arrive at a duality between certain gauge theories. In these lectures it will be conformal gauge theories, and some string theories in some curved spacetimes known as AdS, a spacetime with which you already played a bit in the exercise. Yesterday's argument was based on large n counting, was based on the notion that the graphs, when you have some theory of matrices of size n by n, can be separated into different classes according to the topology on which they can be embedded. So there are graphs that can be drawn on a sphere, that are called planar graphs. Graphs that can be drawn on a torus with one handle, that are called non-planar graphs with genus 1. And non-planar graphs with genus 2 that can be drawn on a torus with two handles, and so on. So as we sum all of them, we associate a cartoon of some Riemann surface with no holes to the sum of all planar graphs, and that scales with n squared times a function of lambda, where lambda is a so-called 't Hooft coupling, which is held fixed as n goes to infinity. We have the graphs that can be put on a torus, and the graphs that can be put on a two-handled torus. And this cartoon, of course, resembles very much our definition of string theory, which is there on the right. So this tells you that a string theory, there should be a description of these 2D surfaces made out of all these Feynman diagrams that are drawn here. They're hard to exist, but of course this is just a cartoon. It's very hard to make quantitative progress along those lines. We also saw that a single trace operator should correspond to a single trace, to a single string, just by the nature of the diagrams we were drawing. And we saw that if we have 4 operators, that is, you can think of it as 4 strings, to leading order in n, the leading behavior is the one given by the disconnected graph, which tells you that to leading order strings prefer to just propagate without interacting, which is natural. And then we have the connected diagrams that start at order n squared. So more precisely, we have this notion of large n factorization, where to large n we have free strings. By free, I emphasize, does not mean by any means trivial. They still have some tension. This is still an infinite set of Feynman diagrams. Lambda is not going to any specific value. The strings still wobble, but they don't split. And then we have effects that are more suppressed in n, that involve either the string starting to interact or even the string itself splitting and joining, effects that are involved to quantum strings in the sense of splitting. And equivalently, we could see that the effect of interactions is suppressed just by computing some normalization invariant quantity that takes into account what is the interaction of a string, and we see that interactions are suppressed at large n. Okay, so on the other hand, what is a string theory? A string theory is nothing else, again, but the sum of Riemann surfaces with more and more holes, where there is a notion of the holes coming with some higher power of the string coupling, so they are more and more suppressed. And I remind you that in that picture, you can exchange n by 1 over g string, because n times g string is fixed. So this is exactly the same as that. And then, what weights each? Instead of a sum of graphs for a given topology, we have a sum of surfaces for a given topology. So it's one-to-one correspondence. And we integrate with the surfaces G. This is a map from the worldsheet to the target space of surfaces with genus. So we integrate over surfaces of genus G. And the action is a two-dimensional conformal field theory, which is given by some tension that tells you that if the tension is very big, the string does not fluctuate at all and just moves along some classical trajectory. And then we have the usual, here I wrote it in Polyakov form, action. And this you have seen in your lecture. So there is some background metric that if you are in flat space, this is just eta mu nu, probably what you worked with. There can be some b mu nu field, and there can be some dilatant that multiplies the 2D curvature of these surfaces. As you might know, the integral of the 2D curvature of a surface just gives the Euler characteristic of the surface, which, as we learned yesterday, was minus this quantity. Remember, don't forget the minus sign, very important. So it was minus this quantity. So you can think that the dilatant defines, if you want, what is G string. If you shift the dilatant by some constant, you are changing your definition of G string. So this is this famous slogan of string theory that even the coupling itself can be thought as just one of the fields of the theory. You just give it some background value and you can think of the coupling in this way. Okay, very good. So now we move into one of the most important arguments in physics, which is the so-called decoupling argument by Maldacena from 97. Okay? Now this is kind of a tough argument, so this will maybe not be the most straightforward, as straightforward as we would like, but it is what it is. Okay. Any question about what we have seen so far? So we started seeing some evidence, and now we will try to start providing some more evidence based on string theory. And as I said, the AdS-CFT duality is not a theorem, it's a conjecture. So we will be as rigorous as we can be, but also I don't want to spend an infinite amount of time in motivating the duality, otherwise we have no time to do interesting checks and to learn more stuff in the last week. And this is annoying me a lot. Why is there a cusp here? Very good. Okay. So now we move into, as I said, a very, very important argument, which probably will take us two lectures just to spell out, which is called the decoupling argument by Maldacena. Okay. So let's try to slowly build into it, and the key idea, or the key, if you want, philosophical principle that makes the duality work is the fact that strings have what is called an open-closed duality. The fact that when you look at a string, depending on how you cut, how you like to think of the string, cutting a diagram in different ways gives different descriptions. Even here, if you cut a diagram here, it looks like a single closed string propagating. If you cut it here, it looks like you have three closed strings. You have this one, and this one. So just from the point of view of string theory, this notion of looking at the different interactions from different points of view can give you alternative description of what is going on, which are, of course, all equivalent. So let's consider the simplest example of all. The simplest example of all can be if you have a brain, so you have two brains, and let's suppose we have an exchange of a closed string between two brains. Okay? Now, how do we think of this picture? So this is a brain, this is another brain. Now, there are two ways of thinking about this. You can think of this as let's see, closed string emitted by one brain and absorbed by the other brain. This is what you would say if you interpret the time as going in this direction, or if you think of the process in this direction, where you have some closed string that propagates and is absorbed by the other brain. Or, if you think of exactly the same diagram from this point of view, or, we have an alternative description, as an open string that is stretched between one brain and another brain, and you have an open string stretched, that moves in time, and time is periodically identified. Okay? It moves in time and comes back to the same position. So we can think of this or as an open string partition function. So there is immediately this duality. In other words, you can think of a brain in two obvious ways. You can think of a brain as a place where open strings can end. This is probably the point of view that we emphasize the most in your lectures. It's a place where open strings can end. But you can also think of the brain as the object that emits closed strings. Okay? So a brain is where open strings end, but it's also, from another point of view, thinking of the same diagrams from another point of view, it's also an object that emits, it's also the object that emits, that produces closed strings. Okay? And this is at the heart of the duality that tells you that you can sometimes think from the point of view of the brain as emitting closed strings. And what does it mean to emit closed strings? It means you can think that it's kind of emitting gravitons into your background and deforming your background. Or it is not, and you think of it from the point of view more of the open string interactions, and then you have some effective theory that describes the low energy interactions of open strings on a brain, which is Yang-Mills theory. So thinking of a brain from these 2 points of view will lead us to a description of brains as open strings, which will be Yang-Mills theory, which is the theory of the low energy dynamics of open strings. Right? You remember an open string contains a photon. If you will have, it also contains gluons, as we will see in a minute, and you probably saw this notion of sham pattern factors. And from the other point of view, this emission of closed strings into the bulk, from the brain into the surrounding space, can be thought of as deforming the surrounding space, generating some effective background, and this background will be anti-de Sitter space. Okay? So this should not be clear at the moment, but give you a feeling of where we are going. Thinking of a dual description of brains, either as from the open string point of view or from a closed string point of view. 2 descriptions that are obviously equivalent, but one which will naturally lead to the notion of deforming a background, because again you are injecting many, many gravitons on your space-time, so you are deforming the metric. And the other that will have an interpretation of studying gauge theory on this brain, which is the low energy theory for open strings. Okay? Does it sound plausible? Of course it's not. I did not finish the decoupling argument yet. I didn't even start. But does it sound plausible as a direction to go? So let's try to go in this direction following a simple analogy. Okay? So this is the main idea if you want. But now let's try to be a bit more concrete and consider some simple examples. Let's consider a proton, which is heavy, and a light electron that is flying by this heavy proton. Okay? So let's think that we have some heavy proton. Okay? So this guy is some heavy proton. And then we have some light electron. Now, how do we study the deflection of an electron past a heavy proton? Well, the electron starts throwing and receiving photons from the heavy guy. So we start drawing Feynman diagrams. And to leading order, we get the Coulomb interaction, which is nothing but the exchange of photons. And then we start drawing other loop corrections to this process. Let's draw a few. And then we start correcting, so we can have something called Bremsstrahlung, which is just the effect of sending together with the electron a very soft photon that you cannot distinguish from just the electron. And then you can have a similar process happening before the interaction. You can have vertex corrections to your interaction. And you can have vacuum polarizations effect. Okay. So this has some name. This is called something I don't know how to pronounce, or even to write apparently. Bremsstrahlung. If there is someone from Germany, he or she can correct me. Then there are vertex corrections. And then there is vacuum or self-energy corrections. Okay. So this is one way of thinking of a process where an electron passes via a proton. We study all Feynman diagrams and we sum all the Feynman diagrams, and the sum of all these Feynman diagrams tell us, so the sum of all this guy tell us how the electron is deflected. Okay. But alternatively, another way of thinking, alternatively, the effect of summing all these diagrams, okay, the sum of all these diagrams, is equivalent to correcting the Coulomb potential. That gets corrected, and it's called something like the Unling potential, the one which is corrected, which is just the Coulomb potential. And then you start correction, and you get some terms, e to the minus 2, mass of the electron times the distance, over mass of the electron 3/2 plus, very good. So we have two options. We have two options. One option is to consider the proton and the electron in pure flat space, in an empty background, and we study all the interactions between them. We sum over all the Feynman diagrams between them, all the photons and so on being exchanged. The other option is we forgot about the proton. We forget about the proton and just notice that saying that the electron moves in some complicated V of R, so we replace this proton by some non-trivial background, V of R, which is now not just empty space. You can think of it as some background away from the origin, where this electron is moving, and the electron just is moving in some non-trivial background, and of course this is equivalent. So we either have the point of view of taking into account Feynman diagram by Feynman diagram, and the proton is there, or we forget about the proton and replace the proton by its net effect, which is to generate some effective potential where the electron moves. Okay, very good. So now we can apply the same kind of reasoning to brains and string theory. We can now have our brain, and this direction can be time, okay? And we can have some closed string that is approaching the brain. At some point it touches the brain, it opens up in some open string, the open string propagates, then can form a deep, and another point touches the brain, then it splits into two strings, and then the two strings can merge again, and then the endpoints can join, and then it can go to a closed string and fly away. Okay. There is some story of a string. It was moving, touched the brain, open string, the open string split into two, the two strings propagate, they join again, and there they go. Okay. Or alternatively, if I want to draw the worldsheet, I would draw something like this, the corresponding worldsheet. This is how I would draw it. Not sure if it is very clear, but this is just the worldsheet drawn by these strings that interact, split, join again, and go away. And then you could imagine summing over all these diagrams, so this interaction plus some interaction with some handle in the middle, plus some interaction where it touches this surface twice, I don't know. Even with some hole, it can be quite complicated. It can have some dome here, and here it can have two. Plus, So this will describe the process of a closed string. So this is our closed string probe that I want to associate. It's the analog of the electron in the previous picture. And one way of studying the way the electron interacts with the brain is by summing all these diagrams, which is the analog of summing over all the Feynman diagrams. But another point of view is to say that whatever this gives, whatever this net effect of this brain is, I should be able to replace this by some propagation of some closed string, eventually with some handles, on the presence of some non-trivial background. So we have 2 points of view in principle. It would be great if we could make this rigorous, and that's what we will try to do. Between a point of view of summing over all these interactions that are described by all these interactions, all these open strings, all this dynamic of open strings that are what describe this brain. That is what you get when you think from this point of view. Or when you think from this point of view, when you cut some surface, you have here some closed string. You see if you cut it here. So this is very much based on the original picture that I presented there. But okay, what we want to do is understand what describes the interactions on the brain, or rather by summing, or otherwise what is the background that the brain creates, in the same way that a charge creates this Coulomb potential. Okay. Very good. So again, let me repeat. If we think in A, we think in this direction. Where we have a description in terms of open strings. And open strings on the brain, open strings on the D brain, which is described by the massless spectrum, which is Yang-Mills, plus massive states. Okay? So these open string excitations, there are some open string excitations that are massless. They describe the fields in Yang-Mills theory. Okay? And then there are some fields which are massive that describe massive string modes. Very good. There are infinitely many. Okay? So this is the description on one side. Okay, plus sources. Because if we start injecting some closed strings, we think that the closed string is like some source that we put by hand, to indicate that something was injected. Then there is an interaction of open strings, and then some source to take out again some closed strings. Okay? So there are some sources that you can think as some vertex operators, some operators that you put, but then the dynamics is that of open strings on the brain, which is given by massless states and then the massive states. Okay? Is it okay? Again, I'm compromising, of course, between trying to be very vigorous and trying to give you the physical picture and then being gradually more vigorous. Okay. In B, okay, we think in this direction. And we think that we have these interactions with the brain, okay, where closed strings are emitted. Okay? Now, emitting closed strings, what does it mean? How do I replace an emission of how should I think of an emission of a closed string on some surface? Well, this is equivalent to thinking that I have my surface. Now I'm closing it. I close this surface here. Okay? And now I say that here I insert some local operator. So I'm using the operator state correspondence to think that in this 2D CFT that describes the string, that I can think of the state that I put here. I can continue the path integral. I can think that I can put an operator such that the state that is reproduced here is the state that I want to get from this picture here. Okay? So there is this picture. Okay? Again, this is more or less a cartoon. I just want to motivate that this can be made precise using this idea of local operator, where by putting these many holes, what we are doing is equivalent, summing over all these interactions with the brain is equal to a sum over insertions of some closed propagation and then a bunch of operators inserted on this closed string propagation. Okay? So you can think that as you sum more and more operators, the net effect, let me hand wave a little bit, but it will, I think, help to make contact with what we know about over there. You sum over all these vertex operators that are more or less independent, so they just exponentiate. And what you will get is something like this, exponential of the integral. You can put the vertex operator any way you want on the Riemann surface, which is to say that the string can interact on the Riemann surface at any point. You sum over where it does. And then some effect of putting this guy, which is some kind of vertex operator, V. The point is that, as you see, what happens is that if you do this inside the path integral, what this has the effect of doing is creating a new exponential that in practice is changing your action. Right? It is just an exponential term that you can think of as modifying your action. Is it clear? It's another exponential. The action is already in the exponent. You just add it to the action. Is it okay? So the way you can think of this is as deforming your action. In other words, changing the background. Okay? It's changing the string theory. It is changing the action. And this is very intuitive. This is just saying, this is equivalent physically, okay, to saying that the condensate of gravitons changes the background. If you inject many gravitons, if you inject a few gravitons, it's a linear perturbation, but as you inject more and more gravitons, you can eventually deform the background by a finite amount. And these closed strings contain many stuff, but in particular they contain gravitons. Gravitons are among closed strings.
Pedro?
Yes?
Can you repeat why you get an exponential there? Why the operator?
No, I mean, just because of thinking that the operators are roughly free, they are indistinguishable. When I put 4 of them, I will put some 1 over 4 factorial, and I integrate over where they are inserted. This at sigma 1, this at sigma 2. So roughly, I would get an exponential. This is by no means precise. Of course, whatever it is, I'm saying that it has an exponential nature. I mean, it is big. It's something very big that wants to be exponentiated. I mean, it is extensive when I write it in the exponent, not when I keep it down. But the picture is that a local operator is a small deformation. If you sum over all the insertions, over all the holes as the closed string interacts with the brane, if you resum them all, you expect some large deformation. So it deforms your background. So you inject many gravitons, you eventually will deform your background. Very good. So let me make one more comment, and then we will try to be yet a little bit more rigorous. So we are approaching somehow some kind of coherent picture, but so far it is very sketchy, so we will get there. I just want to remind you that about this small point that I want to develop a bit more on this idea that there is Young-Mills as described by open strings. That open strings describe Young-Mills. So when you have a string, okay, one second, let me think, what do I want to do? Okay. So open strings acting on a D-brane, they do not contain Young-Mills. I mean, they contain some theory that you can always call Young-Mills, but which is QED, it contains photons. Photons are much simpler. Photons, you have a mu, but a mu is not a matrix, it's a number. Okay, so it's like gauge theory with n equal 1. So how do we get a gauge theory? How do we get an A mu, a gauge field, that has indices ij, like a gluon? Right? So how do we give indices ij to the field? Okay? Did you discuss this in string theory? Did you mention Shan pattern factors? No? Okay, and the idea is very simple. If you have a single brane, why are there strings that are massless? They are massless because they are very close to each other, and okay, let me say differently. If you have two branes that are stretched, then if you stretch an open string, it cannot be massless because there is some tension, so there is some energy. So the string is massive if you oblige it to be stretched. But as soon as you let it live on the same plane, you can have massless modes. Now, you can imagine superposing several planes at the same position. So you superpose several branes. Okay? And this is what is called a stack of n branes. But then you get a new degree of freedom to play with. You can say that your endpoints of your string, this endpoint can end on brane j, and this endpoint can end on brane I. But the argument that told you if it's massless or not, it's still okay, it's still a massless field. I mean, the branes are all at the same position. They are not stretched, so you are not obliged to have some mass. So you get some massless fields naturally, A, mu, which now are matrices and have indices I and j. Okay? So this is the idea of Shan pattern. And this is how non-abelian gauge theories arise as string theory. They arise as the dynamics not of a single brane. A single brane gives photons, but as a stack of n branes. A stack of n branes leads to SUN gauge theories. Whereas a single brane leads to QED, or to photons. Okay? So what happens? What happens to the diagrams So what happens when the string tension goes to infinity? And you are describing a bunch of open strings on a stack of n branes, and you take a very large string tension. Okay? So what kind of things do you draw? Well, very large string tension means that the strings are very small. So let's draw our stack of branes. Okay, but I want to draw actually a big stack of branes. Well, let's draw something fun. Let's have some big stack of branes. Okay, so this is the stack of branes. So there are many branes on top of each other, which means that the open strings, the end points of open strings, they have an index that tells on which brane they are. Okay? And now let's see what happens when some strings scatter with each other. So let's say we have some open string, and I'm drawing the endpoints close to each other. Why? Because the tension is very big. The tension is very big, they don't want to move very far away, they are pulled together. So they want to be close. Is it clear? Tension is big, they don't move far apart. So we have some open string here. Let's draw some open string here. Let's draw some open string here, and let's draw some open string here. And let's start drawing what can happen. So this string can start moving here. Okay, let me not make it wobble, let me draw it like this. This string can move, now it's here. Okay? Now it can move a bit more. But it can, for example, this string can start deforming, and now the end point can touch. Okay? And now it can split into two strings. And here are the string, and here are the string. Okay? And then this string can again split into two strings, and one can go, say, here. And this is again when the string splits into two strings. And so on. So this would be the natural diagram that we would draw if we would start studying this open string scattering. Right? So now this is very familiar. This is nothing but the fat diagram that we were drawing last time. This is nothing but the large n diagram. And indeed, it makes total sense. Let's even check the Chen pattern factors. Where are the strings? So let's use different colors. Let's suppose that this string here, say, is as this guy on leg, this is on brane J, and this is on brane I. Okay? Now, this leg here, it's always on brane J. This leg here didn't change. It's always attached to brane J. It cannot jump. Right? So this leg is always on brane J, and this is J. This guy is always on I, so this is I. But as they split, this end point here, this midpoint here, it can go to it can touch any of the branes when it splits. So this guy here in the middle, it can be in some brane K. And this guy can be in some brane K. Right? And you sum over which brane is it. So you get a factor of n by summing over all these holes in your diagram. Right? And here you have some index L that is running over. Okay? So this is how a gauge theory emerges. You see the diagrams of the string. So this is how the fat line notation or the double line notation. So we recover the double line Feynman diagram expansion. Okay. So when strings start becoming small and behaving as particles, it's the field theory limit. And in this case, we start recovering the FET diagrams of the FET diagram. Okay? Okay, very good. Let me see what else. Okay, so let's stop and let's try to see, so what do we need to do? Okay, so what is our task now? Okay, now our task is to make this precise. So let's list a couple of questions that we would like to answer in order to make all this precise. Okay, yes?
I understand what you're saying there, but I don't understand why is it specific to big N. So I see that for big N, we get that the string theory becomes the same as the QFT. But why does it only work for big N? Or where do we use that we have a lot of stacks?
At this point, we did not use yet. At this point, we did not use yet. What you would see is that if you start drawing diagrams that correspond to topologies where you start drawing holes, it will correspond to drawing diagrams that are non-planar in the gauge theory. Okay? So if you try to follow it, you can try to do it. But for now, because we are just drawing these leading planar graphs, you don't see the difference. So there are some questions that beg to be answered now. There are some questions. We are making progress. Now we are starting to see that from string theory, and we know very well what is the low energy dynamics of string theory. We make contact with our cartoons of large N. Okay? So this has a big potential. Here we can understand very well the low energy dynamics of string theory, so maybe we will be able to tell which string theory is dual to which gauge theory. Okay, but let's see. So the questions we would like to ask now is, what Yang-Mills theory? What Yang-Mills theory describes this point of view A? This is one question. Another question is, what is the background, the analog of this V of R, in the point of view B? Okay. By the way, let me also mention that here we have n branes, and taking n to be very large is the analog of saying that the proton is heavy. Okay? So for our analogy, where we want to have some background which is heavy and some heavy background, it would also be important to consider a stack of many branes. So this is some preliminary motivation for considering many branes, because we want to have some background, the separation between the branes that generate a background and the probes that interact with the brain. Okay? Very good. So we now want to answer these two questions. So let's start by the first one. Let's start by this first question. So we can ask, what is the low energy effective action for the degrees of freedom describing the fields in the brain, in a brain, and also the closed strings that can be moving around here. Okay, there can be some neighbor closed strings. Okay? So, but maybe before, let me ask you, what have you seen about string effective actions? So did you see that you get general relativity at low energy, for example? But you were told this, that string theory contains general relativity at low energies. This you were told for sure, right? Very good. So how can we see? Okay, so then we have to make a detour. Okay. So let's make a detour on string effective action. Okay. actually not much, so maybe it's okay. Okay, so how would you determine a low energy effective action for a string theory? Well, how do you determine any low energy effective action? One way of determining a low energy effective action is you study scattering amplitudes between your particles. Say, you use the rules of string theory and you study how 4 gravitons scatter. And you derive what is the S matrix for 4 gravitons. Right? And then, if you know the S matrix for 4 gravitons, or for 3 gravitons, you start writing your action, your effective action, which would be an integral over 10 dimensions. And then you start writing. You have some graviton, dH, plus some interaction, which is mediated by G Newton, and then some number times some term with 3 h's, schematically of this form, plus tac. And all these numbers you fix by computing string amplitudes. This tells you what is the effective theory for the gravitons. You fix the 3-point coupling by studying 3 graviton scattering and so on. And this is one way how you would compute any effective action. So it's never worth it. This is a 10-dimensional action, nothing to do with the action we start there, which is a 2-dimensional action. It's an integral over d sigma d tau. So you use that action, you compute scattering amplitudes, then you fix your effective action. And then, if you compute many terms, you see that they resum to gravity plus other fields, where this G is just eta plus H. You see that they resum into gravity. So this would be one way of deriving gravity. Or of deriving any effective action. So an effective action, you compute scattering amplitudes and find an action that by construction reproduces what you already computed. So this is one point of view. Okay. Another way of deriving this effective action, it also follows very beautifully by requiring that the 2D string theory is conformal. So what does it mean to be conformal? Conformal means that if you look at the action there, you can think that you have dx multiplying a bunch of stuff. A g mu nu, a v mu nu, a phi, and so on. You think of those as couplings. Okay, so they are couplings that depend on the fields. And you ask, how do these guys change as I change my renormalization scale, as I start renormalizing? So I compute the beta functional for this g, b, and phi. Is it clear? So I integrate out massive momentum modes in 2 dimensions. I generate some beta function. Integrating out this higher momentum modes changes g to g plus some beta function of g times some delta g, b to some beta function of b times some delta b, and so on. Okay? So I can impose that the beta functionals for g, for phi, and for b are equal to 0. This is the statement that the theory is conformal, that it does not develop a scale. It doesn't depend on the scale. Now, because it's a beta functional, this will give me some equations of motion for this metric, g mu nu, for b mu nu, and for phi. And then you ask, from which action do they follow? From this one. So this is the action from which beta equals 0 follows. Totally alternative derivation, and it's beautiful in string theory how everything comes together and gives the same result. Okay? Okay, so there is a way of writing effective actions that are actions that describe the low energy degrees of freedom of your string. Now, these actions are effective actions. Effective from several points of view. From the point of view that you consider, so the point of view that I just mentioned, that you find what is the action that reproduces the computations we want to get, so it's effective in this sense. but effective in the renormalization sense. These are actions that typically you get by integrating out massive modes. So you can trust them up to energies where you start producing those massive modes. Okay? Very good. Okay. Maybe another comment I can make, which is not related to string theory but to physics in general, is that gravity, we know very well from our experiment that gravity is free at long distances. Okay? Gravity, Newton constant, is dimensionful, so you can compare energies with a dimensionful parameter, and if the energies are very low, the effect of gravity is negligible. Just the effect that in condensed matter, we never consider the gravity interaction between electrons. So gravity at low energies or long distances is free. It's the statement that the coupling here is dimensionful, and if you consider energies very small, it makes sense to ignore the coupling. It makes sense to ignore gravity, to consider that there is no gravity, and it also makes sense to ignore the coupling of like Young-Mills or electromagnetism to gravity. Okay? This is just it matches also our physical experiences. Very good. So with this small detour, we can ask, what is the description, what is the effective action, what's the string, what's the action that describes the degrees of freedom from point of view A? Well, there are three parts of this action. As I was now discussing, you can have the action for the 10-dimensional supergravity. Okay? This is the action for the gravitons, for these closed strings, for the massless closed strings. Okay? Plus, now let me add something that I should have said before, which is that you know that brains, there are different brains. There are DP brains. Right? There is D1, D2, D3, D4, D5, whatever. A D3 brain is a brain that has 3 spatial directions and 1 time direction. This is the nomenclature, right? And what are the most interesting gauge theories? They are gauge theories in 4 space-time dimensions. So the ones we are going to consider are N D3 brains. So let's consider this setup. So then we have the 10-dimensional action. We have the interaction action of gravity, of bulk of gravity with brain. And then we have the action of the D3 brain. Wow, I wrote it very big, I don't know. Okay. So what's the action of the, let's start by the D brain maybe. What's the action of the D brain? Well, if you come from superstring, you'll get a supersymmetric theory, and you get a theory that is called N equals 4 super Young-Mills theory, okay, which is a theory that has a Lagrangian, which is integral d for x, and then you have 1 over g Young-Mills square, trace of the field strength square, plus there are other stuff that we will explain carefully in 1 or 2 lectures. There is trace of some scalars, plus It's a supersymmetric Young-Mills theory. Plus higher derivative terms, some L, which will be roughly of the form, let me not write anything, something like some alpha prime integral of some f to the 4 plus These are higher derivative terms that come from integrating out the massive modes. So this is the effect of the massive modes. Again, alpha prime is dimensionful, and all this junk here is irrelevant at low energies. If you want, this is what we saw in lecture 1. As you go to very low energies, you just have a CFT given by your massless modes, which are Young-Mills. Very good. What about the 10D gravity and this stuff? Well, now that I have done this introduction, I think I don't have to say anything. So the point is that, again, if you consider low energies, these guys, they decouple at low energies. Gravity decouples at low energy. Okay. So at low energies, A is equal to a sum of two decoupled systems. So we have on the one hand n=1 super Yang-Mills theory in 4 dimensions. This describes the brain plus supergravity in the ball in 10 dimensions, and they don't talk to each other. Okay, this is what we get when we take this low energy limit. Okay, very good. And this description, I should say, this is a very useful description if the 't-Hooft coupling G, which is G string times N, is much smaller than 1. Then this is a really nice description because Yang-Mills theory is perturbative. So if lambda is very small, when you start drawing diagrams, the diagrams with a small number of loops, they contribute the most, and it's you get a very good description of your theory when the coupling is small. Okay? From the point of view of string theory, this lambda appears very natural. You see, N appears immediately, and G strings is what you put when strings split. So by definition, you reconstruct exactly the expansion in lambda. Okay. So then, you can ask, what about B? Okay? And let me say, what will we find when we will study B? So tomorrow, let me anticipate, what we will do, what we will start by doing, after reviewing a bit what we did today, as usual, we will show that B is equal to string theory in a curved background, which is called AdS5 times S5, plus a decoupled system again, which is supergravity in 10 dimensions. And the wonderful insight is that we can therefore cut supergravity from both sides, and this will be the derivation or the motivation of AdS CFT. Okay? That at low energy there will be two descriptions, one of Yang-Mills plus some decoupled gravity, and the other strings in AdS5 times S5 plus supergravity in flat space that are again decoupled. And therefore, if you have A decoupled with B is equal to A prime decoupled with B, A should be dual to A prime. And this will be how we will arrive at this duality between n=4 super Yang-Mills in 4 dimensions and a completely different theory, which is a string theory in a curved background. Okay, so let's stop here. So how do you feel about the general picture? Just some fireworks? It is what it is supposed to be, just to give you some idea that there are many, many ideas pointing towards this correspondence. But at the end of the day, the strongest motivation is that when we start computing stuff on both sides and doing totally crazy different computations, they will agree. So I think the derivation by itself, if people would then start computing and it would fail, no one would be surprised. They would say, okay, we hand waved quite a bit, so we cannot expect that much. It's the fact that after all this, the fact that there are so many different arguments pointing towards this correspondence and then everything works miraculously that gives us maximum confidence that everything is correct. Okay? But if it feels like it would be better if it could be more rigorous, I'm with you. I totally agree. But again, this is why it is a conjecture, not a theory. Okay, let's continue tomorrow.